So in this part, we'll just focus on formulating the problem logic and converting it into a CNF form so that we can use a SAT solver. Before covering SAT solver, we covered characteristic equations or characteristic relationships. And that's a way of characterizing a schematics, a circuit. You design your circuit. Let's say I have an AND gate, very simple circuit. It has two inputs, A, B, and one output, C. This is just a very trivial example. This is a circuit. How can I characterize, model this circuit in a formula? That is a characteristic relationship, CR for short. Characteristic relationship does not have to be in CNF form. It can be in any form. It just captures the meaning of this schematic. If you have the characteristic relationship, you can retrieve back the circuit, okay? But to use a SAT solver, we require one more thing. So the characteristic relationship must be in CNF form. You might start like what we're covering in the class. Most of the time, you will end up with a CNF form anyway. But if you were to get some other form or do it in a different way, then you need to convert that form into CNF. Any form can be converted into CNF. You can use like De Morgan, you can use a different Boolean algebra to convert any expression into CNF form. This might be hard though, might be like, so it's better, advisable to use kind of follow the examples we have in the slides and try to end up with a CNF form from the beginning. Otherwise, you have to turn it into CNF form. Okay, so now if I have a circuit like this, how do I get the CNF form? Well, we covered this before in the characteristic relationships, but basically, I'm just gonna call it CR1, characteristic relationship 1. This is circuit 1, and I'm trying to capture it into CR1. So I'm gonna say that the output, C, is equivalent to, I have an AND gate, so AB. That's a characteristic equation. How to further simplify this? Well, we can break the equivalence into implication. We already know from before that equivalence means that we have two-way implication. So C equivalent to AB means that C implies AB, and this is an AND, which is very important. This is how we get the CNF form. AB also implies C. This is still not CNF form, but we're not done yet. We can further break the implication as we covered before. This is implication. We can say implication is basically not the first lateral, so not C or AB. This is still ended with not, I'm just gonna take this between brackets, AB or C. And of course we can further simplify this, not C, and I can just break this into two expressions, not C or A and not C or B, and here we can use De Morgan and distribute this. So it will be not A, and the AND here will be turned into an or not B or C. Now someone might ask, how come we were able to break this into this? Doesn't make any sense. Well, just think about the meaning here. What are we doing? Here I'm saying this clause will be true if I have not C or I have AB together. What did I do here? I said if I don't have C or A, and at the same time I don't have C or B. It's basically the same thing. You can review Boolean algebra, but I didn't really violate anything here. We broke this expression into two. They are completely equivalent. So this, let's just make sure I have an or, and I have an and between each of these. So this is CNF form. So this is a CR1 characteristic relationship in CNF form, or you can write it the other way around, CNF form of the characteristic representation 1. Now, this is very systematic, as you can see. So for example, if I have an OR gate, it's just gonna be CR, I can call it 2, this is just a name, right? And that's, for example, C is equivalent to A or B this time, because it's an OR gate, and so on. This gets really systematic. We have some examples in the slides that you can use for sections or small parts of your project, but you should be able to derive this anyway. For the exam, for just, learning, you should be able to carry this out. So it's gonna be C implies A or B, and at the same time, it's gonna be A or B implies C. And then you can further break it to get from CR, characteristic relationship, into characteristic relationship in the CNF form. So this is basically these two steps at the same time. In the next video, I'm going to cover how do we cascade different circuits. So I don't just have one, I have more. And also how do we prepare the input for the SAT solver for equivalence. Because equivalence is a validity problem, and this can be a bit confusing. So I'm gonna go over this in the next video.